AP Calculus AB, Unit 6, Day 1, Office Hours. Most of the problems are odd, so you should check those in the back of your book. Here's the one even problem. Trying to get to focus. So, check it. So, it says exercise 1 through 4, which you got to do 2 of. Both x and y denote functions of t that are related by the given equation. Use the equation and the given derivative information to find the specified derivative. So they're saying that these are functions of time. So they give you an equation. Let's see. They give you an equation. Just focus. Doesn't really want to focus. Let's see. Sorry, messing with the focus. And there you go, that's better. Just didn't know what to do. Okay. So it says A, given that dx dt equals 2, find dy dt. So this is kind of giving you just a warm-up for related rates. You're not having to deal with the word problems and the geometry and all that stuff. They're giving you the relation. They're giving you one of the derivatives, and they want you to find the other. So we got to take the derivative of this with respect to time implicitly. Okay. Plug in my chart. Okay. So we take the derivative of this with respect to time implicitly. So derivative y with respect to t is dy dt, 3 dx dt. Derivative 5 is 0. So there should be no extra term there. You don't have to write it. So in this case right here, then if we plug dx dt in, we were told it was 2, we get 6. So that's our answer. That's part A. Part B says, given that dy dt equals -1, find dx dt. So same idea, other way around. We need the derivative implicitly, dy dt equals 3 dx dt. And we could plug -1 in and solve for dx dt. So dx dt equals -1/3. There you go. All right, number 3, the equation is x squared plus y squared equals 1. They give you dx dt equals 1, and they want you to find dy dt. But they also give you some information. They give you xy equals 1/2 √3/2. Probably gonna need that. So we're gonna take a derivative implicitly. So derivative x squared is 2x, and then dx dt. It's chain rule. We gotta take derivative of what's inside. Plus 2y. Derivative y is gonna be dy dt, chain rule. Equals the derivative 1 is 0. Okay. Now we're trying to find this. We have everything else. So we plug 1/2 in for x. For dx dt, we plug 1 in. For y, we plug in √3/2. And then we're looking for dy dt equals 0. So here the 2's cancel, the 2's cancel. We subtract 1 to the other side and divide by √3. And that's fine. That's good enough for the answer. I mean, if you want, you could rationalize the denominator. It's not too hard. Okay. B, same equation, but this time we're doing dy dt equals -2 and xy equals √2/2, √2/2. Now it's the same derivative, so I think it'd be fine to just jump right into that. 2 times x is √2/2. Dx dt is what we're looking for. Plus 2 times y is √2/2. Dy dt was -2 equals 0. The 2's cancel. 2's cancel. So we get dx dt equals positive 2√2 when you add it to the other side, and then divide by √2. And we get dx dt equals 2. So there you go. Just some kind of getting practice with sort of the steps involved with related rates, but not really getting into it yet. And then the next problems kind of start getting more into the geometry, but kind of help lead you through it. So question number 5 says, let A be the area of a square whose sides have length x. Assume that x varies with time. A, draw a picture of the square with labels A and X placed appropriately. Okay, so we want to draw a picture of the square. A, X, X, X. Square, equal sides, right angles. Right? I mean, that's what you would do anyways if they didn't tell you to, just to kind of help organize the information. B says, write an equation that relates A to X. Okay? A equals x squared, area of a square. So this is what we would usually do next. So they're kind of leading you through it. C, use the equation in part B to find an equation that relates dA dt and dx dt. Okay, so we're going to take the derivative implicitly with respect to time. dA dt equals 2x dx dt. If you don't get a dx dt, something's wrong. Like, because you're probably not going to be able to solve for what you need to. And it says d, at a certain time, at a certain instant, the sides are 3 feet long and increasing at a rate of 2 feet. So 3 feet long means x equals 3, and the sides are increasing at a rate, that's dx dt, of 2 feet per minute. Positive. Make sure you note that. Okay, how fast is the area increasing? So we're looking for dA dt at that instant. So we got to take, we already have the derivative, dA dt, and we just got to plug in the x value, which they told us was 3, dx dt, which they told us was positive 2. And so dA dt equals 12. Now, units on this problem, feet squared, because it's area, over time, which is minutes. There you go. So that one's a little more like what we're doing in class, but they kind of helped you out along the way. Number 6, similar thing. It says let A be the area of a circle of radius r and assume that r increases with time. Draw a picture of the circle with labels A and R placed appropriately. Okay, so we need to draw a circle. Area, r, perfect. That's part A. Part B, write an equation that relates A and R. A equals pi r squared. Cool. C, use the equation to find an equation that relates dA dt and dr dt. So you're going to take a derivative implicitly with respect to time. dA dt equals 2 pi r dr dt. You got to follow it up. So the 2 comes out in front. That's the outer derivative. And then inside there's some function of time that you can't see. So we just write dr dt. Okay, D. It says at a certain instance, the radius is 5 centimeters and is increasing at a rate of 2 centimeters per second. So it's dr dt is positive 2 centimeters per second. How fast is the area increasing at the instant? So we're looking for dA dt. All right, well, we have the relationship up here. So d dt equals 2 pi, the radius is 5, drdt is positive 2. So d dt equals 1020 pi. And the unit should be area. And in here it's centimeters. Centimeters squared gives you area per second. There you go. So kind of helping you ramp up to it. Now we're going to get some problems where you get to just do it all on your own. But you've kind of gotten some practice with the major steps and the work involved. So number 13 says oil spilled from a ruptured tanker spreads in a circle whose area increases at a constant rate of 6 square miles per hour. How fast is the radius of the spill increasing? Now, by the way, I write the whole problem down when I do my homework just because I want to circle stuff, underline it. I'm not going to rewrite it right now. That would take too long to rewrite it again. But we need a picture. It's a circle, right? It has a radius, it has an area. You've been practicing this right on the previous problem. It says whose area increases at a constant rate. So they're giving you dAdt. This is the least of what you should do. If you're not going to write the whole problem down, at least summarize the important information and label it 6 square miles per hour. Okay. And it says how fast is the radius increasing? So we're looking for drdt. It says when the area equals 9 square miles. So we're probably going to need to use that area equaling 9 to help us find maybe like the radius at that time or something. Sometimes they just straight out give you, oh, when the radius is this. Okay, so we need a relationship between dAdt and drdt. So we need a relationship between a and r first. A equals pi r squared. Then we take the derivative implicitly with respect to time. 2 pi r drdt. And we plug in what we know. We know 6 for dAdt. We don't know the radius. So that's the one thing that we need to find. So the area equals pi r squared, right, which equals 9. And so we divide by pi. And we take the square root of both sides, plus or minus. We could leave it like this, 3 over square root of pi. Put that in, 3 over square root of pi. Now, when we do that, let's see what happens. This and this reduce to square root of pi on top. And then we need to divide both sides by that. So we have 6 divided by 6 square root of pi. And so drdt equals 1 over the square root of pi. Or you could rationalize the denominator, square root of pi over pi. The units are radius, 1 dimension, miles to the first power, over time, which is hours on this problem. So there you go. Okay, number 15. And some of these should remind you what we're doing in class. Number 15, a spherical balloon is to be deflated so that the radius decreases at a constant rate of 15 centimeters per minute. At what rate must the air be removed when the radius is 9? So we're dealing with a sphere. So we draw a quick picture. It's got a radius. It's got a volume, right? So we're probably going to be dealing with the volume. What information do they give you? It says the spherical is deflated so that its radius decreases. drdt equals, now it just says 15 centimeters per minute, but it said deflated, so that means we're losing radius, right? The radius is getting smaller, so you need a negative on that rate. They're not going to usually give you that negative. It's going to be described in a word, decreases, deflated. At what rate must the air be removed? So we're looking for dBdt. Air being removed is volume of air. And it says when the radius equals 9 centimeters. So that pretty much summarizes the problem. So we need a relationship between volume and R, V and R. So the volume of a sphere, which we didn't know, so it's 4/3 pi r cubed. Makes sense that you have an r cubed because you need 3 dimensions for sure. And there's a pi, of course, and r. The 4/3 is probably the hardest part to remember. And we got to take the derivative, dv dt equals, multiply by the 3, power rule, 4 pi r squared, dr dt. And the radius is 9, and dr dt is negative 15. So it's kind of a big number. Let's see if we can do it without a calculator. 4 times 15 is 60. Times 9 times 9 is 81. 0. So then 0, 6, 48. So dv dt equals negative 4860 pi. Don't forget the pi. Volume is cubic centimeters, and time is minutes. Now, the only thing I would say is that they asked the question, they said, at what rate must the air be removed? So I would say the air is removed at a rate of 4860 pi cubic centimeters per minute, and not put the negative, because the removed word implies the negative. Okay, so the negative probably isn't the most exact best way to write this answer because of the way they worded the question. Okay, if they said, at what rate is air being added, and you give a negative answer, then that would imply the opposite of adding, removing. But removing already implies the negative. Okay, 17 says a 13-foot ladder is leaning against a wall. If the top of the ladder slips down the wall at a rate of 2 feet per second, how fast will the foot be moving away from the wall when the top is 5 feet from the ground? So this is like one of my nightmares when I get on ladders. One, either you're going to fall backwards, or the ladder will slip down here and fall this way. Now, as the ladder falls this way, sliding down the wall, this end of the ladder goes outwards, right? So it's good to add some arrows to movement here. So look, this is the ladder. Now, what information they give us? 13-foot ladder, so it's 13 feet no matter what, long. The top of the ladder slips down the wall at a rate. So this rate is 2 feet per second. It's going down the wall. How fast will the foot be moving away from the wall? So we're trying to find this one right here. So we got to create some variables. You can use whatever letters you want. X, Y, Z, A, B, C, but you got to label it, because if I put A here, you might put A there. I'm going to say A, B, C for right triangle, Pythagorean theorem dots in my head. How fast will the, okay, so we're looking for essentially dAdt, right? As A gets longer, for the ladder moves out here. And this is dB dt, and it is negative because B is getting smaller. We got to relate these. So we need, now by the way, what's dc dt? dc dt, the length of the ladder, is 0. It's not changing. We need a relationship. A squared plus B squared equals C squared, right? And if we take the derivative right now, 2a dAdt plus 2b dB dt equals 2c dc dt, and then plug in what we have. Now it says when the top is 5 feet from the ground. So 5 feet is this instance. Okay, so we can plug that in now. So we, oh, you know what? We got to figure out what A is from the Pythagorean theorem. So a lot of times the relationship you use to relate the derivatives is also something you need to relate just the lengths to get them. So we got to do a quick little, well, actually it's, yeah, we got to do a quick little Pythagorean, or Pythagorean theorem. So let's see. Or did they tell us that? No, I don't think so. Okay. So A squared plus B squared equals C squared. A squared plus 25 equals 169. a squared equals 144, square root of both sides, plus or minus is 12. So we got that now. All right, so a is 12. Now dA dt is what we're looking for, plus 2 times b is 5, dB dt is negative 2. If you don't get that negative right, you're at the wrong answer. C is 13. dC dt, though, is 0. It's not changing the length, so it goes away. All right, so 24 dA dt equals, this would be negative 20, so I'm going to add it to the other side, positive 20, divide both sides by 24. dA dt equals, we could reduce this, 5 over 6. The units of A are feet, one-dimensional over time. This problem is seconds. Now, I don't know if I'd box the ADT, but, you know. The other way to do this problem, by the way, is if there is a constant, something that's not changing. Now, you can't plug 5 in for B at the beginning, but you could, before you even do the derivative, plug the 13 in for C, and then take the derivative, which would give you a 0 really easily right here, which is definitely nice. Okay, so I would do that. But you can't plug B equals 5 in before you do derivative because B is actually changing. You can only plug numbers in for things that aren't changing before you take the derivative. All right, last one, 27. Sand is pouring from a chute. Forms a conical pile whose height is always equal to the diameter. If the height increases at a constant rate of 5 feet per minute, at what rate is sand pouring from the chute when the pile is 10 feet high? I mean, these problems can feel a little overwhelming. You got to break down, you got to draw a picture. So conical pile is a cone upside down. So I would draw a picture. Now cones have a height and they have a radius, okay? And it says sand is pouring onto it. So the pile's getting bigger. It says whose height is always equal to its diameter. So h equals d or 2r. Maybe radius might be more helpful at some point. I don't know. If the height increases, so that's dh dt, is getting bigger, which makes sense as the pile gets bigger, 5 feet per minute. So I'm writing down all the information. So that's dHdt at a constant rate of 5 feet per minute. What rate is the sand pouring down the chute? So the sand pouring is volume. So we're looking for dVdt when the pile is 10 feet tall, 10 feet high. Okay, so that's all the information right there. So we're trying to find dVdt. So we need a relationship between the volume, h, and maybe r. And so the volume of a cone is 1/3 pi r squared h. Now here's the deal. We don't want to take derivatives yet with 3 variables because it's super messy, but they give you this key information. So we're going to plug that into h so that we're going to rewrite our equation so it's all one variable, which is always desirable if possible. Okay, so our volume equation is now 2 pi over 3r cubed. Is that right? Wait, hold on. It says height is always equal to the diameter. Height is equal to the diameter equals 2r. Height is equal to the diameter. Oh, but hold on. We have dH dt, so this is fine, but we really want all h's. Okay, so that's not what we want. We want all h's since they gave us the HET. I think that's just the easiest thing. I mean, we could do this, but so r equals, if h equals d equals 2r, then r equals h over 2. So that's what we're going to plug in for h. So the volume equals 1/3 pi, and we're going to plug in h over 2 and for r squared. Now the h over 2 gets squared. All of it gets squared. So that's going to be pi over 12, 2 squared times 3 is is 2 squared is 4 times 3 is 12. H cubed. That's the volume equation we want to use. So we're going to take the derivative, dv dt, and we're going to get 3 pi over 12 h squared dh dt. And so pi over 4, the height is 10, they said, at this instant. We can't plug that in ahead of time because it's changing. DHT, they told us, was positive 5. I'm always double checking positive or negative. It's so easy to make that mistake. That's going to be 100 over 4, so that's going to give you 25. And so dV/dt equals 125 pi. The units for volume should be cubic feet. And time is minutes. So there you go. Came out positive like we thought it should. And that's it. So we'll start to do a little more challenging problems in the coming days. So this is good practice. These are challenging problems, but they're kind of fun and interesting. There you go.